we're talking about OTM transport. The first name to mention is always, when you talk about OTM transport, is always Gaspard Monge. Yeah. So Gaspard Monge introduced the OTM transport problem a few years before the French Revolution. And the problem that he was investigating had to do with military applications. So you have a certain amount of material that you extract from the ground that you want to build fortifications. And essentially you want to do this in an optimal way. What does it mean to do it in an optimal way? The idea is that if I want to transport material, there will be a cost associated to transporting. It could be workforce, because people have to do it. Maybe I have to pay people, it depends. But in any case, there will be a cost. And then given once I decide the cost, I can then ask myself, can I transport the material in the most efficient way? So back in his model, Monge considered the travel distance as its cost, which means that if you have to move, so we're in the US, if you have to move 1 pound of material between two cities that are, let's say, 100 miles away, I will pay 100. If the cities are 1,000 miles away, I will pay 1,000, okay? And if it's 10 pounds, I will pay 10 times more. So you pay proportional to the distance, the number of kilometers, and then the unit of each unit, this is what you pay for each unit of mass. This is the simplest OTM transport model. This is called now the Monge problem. So Monge wrote some very nice memoir, and where he studied this problem both in 2 dimensions and 3 dimensions, and he wrote a series, several very interesting geometric considerations that have then been used almost 200 years later to really solve mathematically the Monge problem, which is actually one of the most challenging ones from, let's say, from a theoretical viewpoint to understand how to solve the Monge problem. But essentially, you see, Monge was working on this at the end of the 18th century, and once the 19th century started, mathematicians had many other things to worry about. They were still discussing about foundation of geometry and many other things. So OTM transport was not really under the radar. And we had to wait 150 years before really a big new revolution came, and this was with Kantorovich. So in the 1940s, Kantorovich understood how to mathematically reformulate the Monge problem in a way that now we call a sort of non-deterministic transport, or the Kantorovich approach to OTM transport. The key point of Kantorovich was not only to, now I will explain in a moment what Kantorovich did, but let's say the key problem of Kantorovich was to transform a mathematical problem, which was the Monge initial one, into something which was very treatable. It became a convex problem. It became a problem that he could solve with linear programming. So he has been the founder of linear programming. So for application, it's really been extremely important. But let me just now explain what the idea was. So in Monge formulation, essentially Monge was not allowing to split the mass. So the idea was that once you decided that some amount of mass was at location X, whatever was at X had to go at a decided location which was Y given. So all the mass that was in some location had only one possible destination that could reach. But you see that if you have a simple problem like this, where you think that the bakeries are the one that produce, let's say, bread or croissant, and let's say you have bakeries that produce croissant, they want to send it to several coffee shops in the city. And of course, it makes no sense that a single bakery can only send croissant to a single coffee shop. That would be totally useless. So the idea is that a single bakery can supply multiple coffee shops, and a single coffee shop can get croissant from more than one bakery. And the idea is that you're looking for a global optimum. So here there is not about competition, there is no pricing. The goal is just that you minimize the total transportation cost. So it's a cooperative well-being. You want the well-being of the total environment, let's say, by minimizing the transportation. So the idea, you see, you have arrows that you have to connect the different bakeries and coffee shops. A single arrow will tell you at the same time if some croissant go from one bakery to a coffee shop, and also the intensity of the arrow tells you how much it goes. So the data of the problem are, you know how many croissants are produced, you know how many croissants each coffee shop needs, and now you have to find these arrows. Of course, if you have like, whatever, 10 coffee shops and 4 bakeries, the problem doesn't look so complicated. But we'll discuss later that there are problems of interest where maybe you have 1 million to 1 million, not of course bakeries and coffee shops, it's different. And then, you know, starting to put arrows between a lot of possible configurations is not such an easy problem. So for his work, Kantorovich received the Nobel Prize in Economics in 1975. So it has been very influential. But let's say until now, the optimal transport problem was still a problem mostly for economists. And it really became a math problem, I would say, or let's say it attracted the attention of the math community, I would say, in the middle of the 80s. So Ruscher, Raschendorf, and Brenier were the really people who gave a boost to it. And after the work of Brenier, many other mathematicians, McCann and so on, it really became then a very established mathematical theory. So by now, optimal transport is a bit of everywhere. And I will just discuss a few applications. Of course, you have the standard urban planning problem that you can just say, okay, I know where people live, I know where they go to work, I want to build infrastructure that minimizes the total commuting time or something like that. But it also appears in areas that where it's less obvious why it should be there. And I will comment on some of them. As discussed before by Dima in the introduction, in 2018, after I got the Fields Medal, then many people asked me, what did I do? Not mathematicians, but no mathematicians. So, okay, you got this prize, we didn't even know that they exist. That was the comment, of course, of many journalists. They don't even know the Fields Medal exists. But then after they know they exist, they ask, okay, what did you do? So you try to explain to them what is optimal transport, and it's not always so easy. And then at some moment, few months later, there was Leo Ortolani, who was an Italian comic producer that was doing some comics in Italy about Scuola Normale Superiore, which is where I studied as an undergraduate. And then he took the occasion to say, okay, I'm talking about Scuola Normale, let me talk also about Alessio and explain to the general public what Alessio did. And so here he explained to me why he explained to everyone why I got the Fields Medal, because I understood the best way to go from one place to another, and you can see myself there, using public transportation without paying the ticket. So that was my solution to the OT problems. I strongly discourage you to do that, especially in Zurich. Fines can be very, very high. Okay, so this was one problem I solved. Next one. Another problem where optimal transport appears, although it's not obvious, and today I will try to just hint something, and then in my lecture tomorrow I will be a bit more mathematically clear of what I mean, is a connection between optimal transport and something else. And to discuss something else, I first need to tell you about Dido's legend, that maybe many of you know, but maybe not everyone. So Dido was a queen, and she has many legends in the mythology. There's always drama. Someone dies, someone is killed all the time. So here in this case was Dido's husband who was killed by the brother of Dido. And so she had to escape and flew with the servants away from her country. And then she sailed across the Mediterranean. And eventually she landed on the realm of King Jarbas. And then she asked the king to buy a piece of land where she could found a new city. So she arrived there with a certain amount of gold to give to the king. And the king kind of tried to mock her and say, sure, for this amount of gold, I will give you as much land as you can enclose in a single ox hide. So you see the skin of a bull. Which something that looked like a terrible deal was something that Dido accepted, surprisingly. And then what she did was to cut the oxide into very thin strips. So you see that the deal was very clear, as much land as you can enclose in a single oxide. But then Dido took it to the letter. She cut the oxide. She made very thin strips. And then what she did was to sew them together to make a very, very long cord. And once she had this very long cord, then she said, okay, now let's see how much land I can enclose. So now she had something which was long a few kilometers. And she had to decide now the shape that she should give to this cord in order to enclose as much land as possible, so to have a lot of space to found her city. She did it, and that's what she did. She drew essentially a semicircle on the coast, and then she constructed her city inside, which was Carthage. Good. So you see, essentially what Dido did, sounds, I guess, was she solved a mathematical problem without knowing that, because she was just trying to do the following. Given a curve of certain length, enclose the maximum amount of area. Right? That's just a classical isoperimetric problem. Well, not so classical for her. And she understood the solution. The solution to this problem, is just given, you see by this picture, it depends where you are. So if you're on the coast, you can take advantage of the sea, and then you're going to draw a semicircle on the coast. That's better than what you can do in the hinterland, because in the hinterland you cannot take advantage of the coast, and so then the solution is a circle. And in fact, it's not surprise if you see, for instance, most cities in Italy, when you look at the city centers, they're all round, always. And that's not surprise, because even if you don't have to pay any king to build your city, once you decide how much area you have inside, you want always to minimize the perimeter, because you see the shortest the perimeter, the easiest is to defend from other people that will try to attack you. So Dido solved this problem. So you see, given a curve of certain length, enclose the maximal area. And this is just the same as the following. You can fix the area and minimize the length. So just a dual version of the same problem. Okay, so where is octal transport? We don't see it yet. But I wanted to write this second formulation, so minimize the area with minimize the length with fixed area, because given now this formulation, I can go to higher dimension. In particular, I want to go to 3D. So what will be this formulation in 3 dimensions? It will be fix the volume and minimize the surface. Okay, now you have a 3-dimensional object in the space. You tell me how much volume there is, and then you want to minimize the surface area. The answer to it, well, I guess you all know, but we encounter that even as kids, because when we play with soap bubbles, what happens is just the following. You have plastic wire, and then usually what you do is that you put some film on the wire, you start to blow air, and then what happens, the moment there's this soap bubble will detach from the plastic wire, and the moment the soap bubble closes itself, the amount of air inside is fixed, because the air is not allowed to enter or exit anymore. So you have fixed the volume enclosed by the soap bubble, and then what the soap bubble will do, it will be very wiggly for a few seconds, and then immediately it will become round. And the reason why it becomes round is because it wants to minimize the energy, and the energy is exactly the same as surface area for a soap bubble. So nature suggests that if you are in 3D, soap bubbles are the solution to the isoperimetric problem, again. And in fact, this is true in every dimension if you just formulate it correctly. Although it's not such an easy theorem to prove. So even in 3D, this was only proved in the mid-50s of last century, so it's not something so obvious. because you have to even to give a meaning to volume and area is something very challenging mathematically. While 2D is easier. Good. So where is optimal transport yet? I didn't explain to you, but now we can get to there. So the principle here, you see, is that in all these shape, in soap bubbles, there is an energy, which is the surface tension of the bubble. And of course, nature wants to minimize that. Okay? Now, this principle is actually something even more general, and this is something that Gibbs realized in 1878. Is a principle which not only applies to droplets of like some bubbles, droplets of water or whatever, but also to crystals. All these objects tend to have a shape, which could be a sphere, it could be, well, crystals are three-dimensional, so you will not see a crystal like a pentagon, but you see what I'm aiming for, right? They could have a polyhedral shape in 3 dimensions. And the reason why they have this shape is because they minimize some energy at fixed volume. So there is the same physical principle that governs the shape of bubbles is also the one that governs the shape of crystals. You need just to change a bit the formulas. So of course it cannot be the same energy as for a bubble, otherwise it would be round. But modulo, changing a bit the math behind it, the principle is the same, the formulas are very similar. Okay, now this is very idealized. So the fact that the soap bubble is a perfect sphere, or the fact that a 2-dimensional crystal is a pentagon, is very idealized, because of course I'm not taking into account the fact that in nature there are other forces acting on it. If you take a soap bubble, there will be wind, there will be gravity, there will be other forces that naturally will deform a bit the object. So it will never be perfectly a sphere. And then you can ask yourself, okay, if I know the amount of forces that are acting on the system, can I understand how much the shape changes? This is a kind of stability question. So the question is, can I completely destroy the physics of the system by adding very little energy, or does little energy can only slightly perturb the system? This is a physical question that you can also formulate mathematically. And now let me discuss it for crystals. And that means, just because I think I like more to draw the picture in this way. But tomorrow I will explain to you mathematically what this means, and I think everything will make much more sense for mathematicians, or let's say, for scientists in general. Here I'm just trying to give an overview. So how much the shape will change? So the idea is the following. You see, you start from your crystal, it's very idealized. Here it's like, let's say, super cold, 0 Kelvin. Then you start to add a bit of energy, very little, like adding temperature. So hot just means a bit hotter, not much more. And then the shape will change in some new shape. So from kappa to kappa epsilon. Epsilon is just a small parameter that denotes the energy of the system. You think of very little energy. And this change will shape this shape will change a bit into this kappa epsilon. Okay, this wiggly shape probably you will never see it in nature, but let's say I have to draw something. Okay, so you see a new shape, and the question you ask yourself is, if the only data I'm given is this number, can I predict how much that shape differs from this shape? Do I have some theorem that tells me, oh, that shape can only change at most by so much? This is the only data here. Plus, I know what is kappa. So this problem has a long history. In the sense that this is a question of stability of these physical systems. And optimal transport here can give us a way to kind of incorporate this transformation. So the idea is that when you kind of change from this configuration to this configuration, a crystal is made of infinitesimal particles. And then you can think, okay, let me look at the transport, at the optimal transport between that shape and that shape. I can transport everything. As a mathematician, I'm happy to transport everything. I don't have to transport physical objects. So I can transport a pentagon to this shape. And then this transport kind of encodes the change in geometry. And then you can ask yourself, okay, using this transport map, can I answer the question I raised before, which is, can I predict how much the shapes changed between the two configurations? So this is something that we did a while ago now with Monge and Fratelli in 2010. So what we proved is that the shape of the crystal can change at most by square root of the energy. Okay? What does it mean? It means that if you take this image, you move it to overlap with this other image, they will overlap a lot, but not perfectly, and the lack of overlapping can be controlled by square root of the energy. And the same actually applies also to crystals, to droplets, to soap bubbles. So there's always square root of epsilon. So our theorem is a general result that tells how much the shape can change.
It's just an MC for 3 years ago.
This is in ND. This is an n dimension. So tomorrow I will discuss it again. So the picture is 2D because I don't know how to do it.
So square root doesn't mean d equals 2.
No, square root is every dimension. So in every dimension, you have always this phenomena. And the square root is optimal. Of course, and this is the best you can prove in general. Of course, when you look at this theorem, you realize that, at least in the case of crystals, it looks a bit too weak. What do I mean by this? That in reality, crystals minimize some energy, I told you, that you can write explicitly. There are very precise formulas for the energy of a crystal. And you don't expect ever, even if you have some external forces acting on the crystal, to see a crystal like this, a wiggly one. I don't think that makes sense. So that was something that bugged me a lot for many years. And actually, together with Maggi, like a couple of years later, we could actually prove that this doesn't happen, but only in 2D. And it has been only 10 years later that with Yi Zhang, we actually proved that in every dimension, the crystalline structure never changes for small epsilon. What do I mean by that? It means, for instance, I'm drawing for you a 2D picture, but there is an analog in every dimension. So if your ideal crystal was a pentagon, if you give a little energy to the system, the new crystal will be still a pentagon. You cannot destroy it for small energy. In addition, each sides of the pentagon are parallel to the original sides. So the sides can only move parallel to the original configuration. They're not allowed to change the angle. And then if you were, I don't know, in 3D, and your original crystal was a cube, the only thing you can do is to move the sides parallelly. So that it will be a parallelepippedoid. I hope it's correct. So there is a very strong rigidity. Yes?
But in 3D, is there a physical reason for that? In the sense that the extra energy will presumably be transmitted equally to the atoms in the crystal, and so they each move by some fraction of epsilon?
Yeah, well, so the point is this. When you have a crystal, the surface energy has a formula which essentially gives, let's say, less. So the energy of a crystal depends on the normal. That's the key feature. While on a soap bubble, every orientation of the normal doesn't change, so it's totally isotropic. In a crystal, the direction of normal plays a role in the energy. So if you change a bit the normal, the energy changes. And so the idea is that if you so here you have a perimeter, and you have a surface energy, and the surface energy will predict these normals. Now here, all I'm allowed to do is to perturb the system, but with some external forces which are like volume type, so like gravity. I'm not perturbing the surface energy. I'm only perturbing through some energy which is let's think of gravity, gravitational forces. Every force which is depends on the volume of the system, not on the surface. And now with these forces, you're never going to be able to break the orientations. That's what the theorem says. Which in 2D it's rather easy. It's the proof is really half a page. But in any dimension, to show that you cannot do that is actually rather tricky, because there are some, for instance, it's not so obvious, for instance, that if I take a cube and I chop off a bit of a corner, I cannot do something better, or things like that. And that's something that in 2D is very easy to show that it cannot do it, but in a 3D is more complicated. And so that's what the theorem says, that actually it's not energy convenient to destroy the faces. You can just move it.
In your previous theorem, you wanted to have two shapes which are, like we say in topology, are topologically equivalent. The previous theorem.
No, there is no.
Somehow.
The theorem. Oh, sorry, I went in the wrong direction. So the theorem just says the following: you take the ideal shape, let's say a pentagon, a circle, a sphere, depends which dimension you are, or a ball, and you take the new configuration. The new configuration could be, anything. It could be an object which a priori could have holes, could have extra small connected components here and there. I have no information. The only information I'm giving to you is that the energy is at most epsilon more than the previous one, the total surface energy. So I'm only allowed to increase the surface energy by epsilon. And then I'm telling you, okay, here I made it easy, but let's say I'm telling you that when you overlap the two shapes, there will be square root of epsilon close, which is not incompatible with the fact that there could be some small pieces here and there scattered in the space. So that could, they will never do that, physical systems, but I say from a mathematical viewpoint, nothing forbids that. You're welcome. No more questions. Okay. So this was a case where you see optical transport was connected to a problem, the superimetric problem, which a priori was not at all nothing to do with it. So this connection, we didn't find the connection to optical transport, so let's give credit to the people. Tomorrow I will be more precise, but let's say the connection was found first already in the 50s, not with optical transport, but still to transport theory, and then has been rediscovered in the 80s. But then to apply it to prove this theorem, that's what we did in 2010. So a second problem, if you remember, I gave a list of possible applications of optical transport. It was meteorology. So I'm happy actually to do this, because this was very fashionable when we were here in the 2008 workshop. Actually, a lot of people were discussing semi-geostrophic back then. And so the semi-geostrophic system is a very classical model in meteorology, and is used to describe large-scale atmospheric flows. I will kind of simplify the picture. I didn't write the formulas. As I say, I don't want to put any formula, but let me try just to give you a sense of what we are trying to do. So when you study large-scale phenomena in meteorology, let's say you have a big bunch of clouds that move across a continent and so on, you have some data, which is usually the pressure of the cloud, the pressure of your cloud, the velocity of the particles, and so on. You have these microscopic informations. And you want to predict the evolution in time. So you want to understand what happens as time passes by. Now, it turns out that at least in the semi-geostrophic model, there is another way to understand this evolution, and you can do it at the level of the individual particles. So let's do the following. I take my cloud, and I take a picture of it at time t0. Then 1 millisecond later, well, maybe 1 second later here, I take a picture again. So now I have two pictures of the same cloud, just slightly apart in time. And then I remember that the clouds are made of small droplets of water, so small drop of water, billions of them. So now I'm just putting 20 of them on this picture. And then I know that these 20 droplets of water, 1 second later are dead. But I don't know which droplets on the left corresponds to which droplets on the right. And now the question is, just by looking at this picture, can I say which one on the left corresponds to which one on the right? So, okay, if you have 20 only, maybe you can even try to guess a bit, right? Probably this one all to the left corresponds to this one here probably goes here, and so on. But if I give you a billion of them, I don't think you will do it so easily. And it turns out that Mike Cullen, a British meteorologist in the beginning of the 90s, understood that optical transport will give the answer here. So the way you have to do this pairing, so this coloring from left to right, is by solving an optical transport problem. What do I mean here? You want to find the pairing so that the total cost to transport that configuration to the left to the one to the right is the least as possible. Okay? So just to be slightly more precise, when you talk about optical transport, you have to decide the cost. I told you for Monge, the cost was the distance. In this problem, the cost is not the distance, but distance squared, which is like kinetic energy. V squared, D squared. Right? It's a kinetic energy. So if you take among all possible coloring, the one that minimizes the sum of the distance squares when you do the pairing, then you will get the right movement of the individual particles. Of course, I'm cheating a bit, because you see, when you have clouds, the cloud is a moving process. So the way I should do it is the following. I will take my cloud. I will take a picture of my cloud every millisecond. I solve the optical transport problem many times, because I have a lot of pictures. Each time from one picture to the next, picture to the next, picture to the next. So I have a lot of optical transports. I combine them together, and this gives me an approximation of the movement of the clouds, because of course I cannot do it, then I should do it again, not 1 over millisecond, but 1 over a billion seconds, and so on, closer and closer, and then pass to the limit. So it's like a concatenation of optical transports. Okay, but theoretically that's rather interesting, that I can understand the movement of the particles via this kind of optical transport process. And perhaps what people wanted to do, it was like the hope of the OT community back then, was to say, okay, maybe using optical transport, we can solve the semi-geostrophic system, which is a system of PDEs that is rather complex. There have been many, many results on that. But let's say to really give us an answer to the semi-geostrophic system, there was a problem. So the connection between optical transport and semi-geostrophic has been known for more than 20 years. I'm talking the past, no? But something was missing. There was a problem on a theorem regarding the regularity of optical transport maps. So this kind of the pairing that tells you x goes to y. That was missing in order to really apply that. So I remember when this problem was first proposed to me by my PhD, one of my two PhD advisors, Luigi Ambrosio. I remember very well that he said, oh, there is this problem which looks very interesting. There is a semi-geostrophic problem, there is this connection. That's the theorem that one needs to prove. I was like, oh, that looks cool. I have no clue how to prove it, but it looks very interesting. So I remember that, it was 2005, I started to prove, to try to do something, and of course I failed. Then over time, I went over and over to try with new strategies. I read a bunch of papers about regularity of optical transport, hoping to get some insight. Didn't work, but I learned a lot. And then I was going back and forth, and at some moment I felt I was making progress. So it's like, you see the mountain there, you see the tip of the mountain, and you know that you want to go there. That's your theorem. You want to climb it. And then you try to take a path, and at some moment it seems you are going up, and you get excited, then you get stuck. And then when you get stuck, the most difficult part is that you don't know whether you are on the right path, but just you have to, go on further and persist, or you just are on the totally wrong path. And then you need to go down and start over again. So I can tell you by experience that most of the time, I don't know how to get to the tip, but at least in this case, after 7 years, we understood with Guido De Filippis how to go there. And the final strategy had nothing to do with everything else we had tried for the previous years. So it was really like a new strategy was completely. So we developed this theory for the reliable optimal maps that then we used with Ambrosio and Colombo to kind of give a solution to the semi-jostrophic equations. So yeah, I like this method for maybe now that I'm in Switzerland, especially, this using mountains as an example. It's probably not so pertinent in California. I'm not sure. There are many mountains here. I should put something with surf. I don't know. So, now just to come back to something historical, right? So I told you, so Leo Ortolani explained to you what I did, especially, okay, I explained to you also something else I did, but he explained to you how to get the Fields medal. It's just don't pay the ticket, that's one way. But then once you get it, then you try okay, for mathematicians, it has a meaning. For non-mathematicians, doesn't necessarily have a meaning. So one of the main achievements for me was, at least from the eyes of my friends in Rome, was the fact that one of my favorite soccer players gave me a T-shirt with the signature. So it's Francesco Totti, for those of you who know about AS Roma. He won the World Cup 2006 with Italy, long time ago, but maybe some of you heard about it. So that was, the biggest achievement ever. There, something at that moment, my friends were like, "Oh, wow, that is really important." But then there was another one, which was also very important, at least for Italian standards, which is Uncle Scrooge. It's a Topolino, Mickey Mouse. It's a very important thing in Italy. So as a kid, everyone reads it. And here, there is a story. You see Walt Disney on the top. There is Uncle Scrooge here. And here you can see me there. That essentially, what happened is that they, okay, I don't remember the name in English now of those who always try to steal the money from Uncle Scrooge, but what they did is that they used optical transport in 4 dimensions to take the money out of Uncle Scrooge. Because if you're in 4 dimensions, you can go around the walls of its building and enter inside without having to create a hole, and then they used 4-dimensional optical transport to steal all the money. So this was a story that went on the Italian version of Mickey Mouse in 2022. So that was now the tip of that. So you can use optical transport to steal money if you know how to use the 4th dimension. That's another application. But there are also other things that you can do. And one thing that made optical transport also kind of a very flexible tool is the fact that you can use it to define a distance between distributions, for example, probability distributions. So let's say that I have some amount of mass represented by this distribution that I will call mu. So mu just represents a distribution of mass. And you want to transport it so you want to transport mu to nu. Now it's just 2 distributions of masses. You're just trying to move them optimally. You have a cost function C that can be anything you want. Okay, actually, I'm writing one formula in my slides. So, and then you define the optimal transport distance between mu and nu by, okay, for mathematicians this makes sense. For non-mathematicians it just means, let's say, the minimal. So you look at all possible way of moving mass from mu to nu, and then to move 1 unit of mass from x to y, you pay cxy. So c is the cost that tells you how much it costs to move 1 unit of mass between 2 points, and then you just average. You just add up all the total costs. So among all possible way of transporting, you just take the least possible cost. So that's the optical transport distance. I hope it makes sense even for non-mathematicians. Just the cheapest way to move mass given a cost function. What you can do with that? Well, one of the first, I would say, applications outside of mathematics was a few years ago. This is now a bit outdated, but I think it shows something that was not obvious at the beginning, is that you can use that, for instance, to transport colors between images. So it started to be used first in image processing. So here what happens, you see for each, so you have to look at them in rows. So there are 3 rows here. You can start from the bottom one. This is the source image, and what you want to do here is to take this image, but then extract colors from this one and transfer them here. And you're going to do this by using some sort of optimal transport at the level of histograms of the 2 images. That's the outcome, and then there was a small filtering to clean it up. And then, for instance, you see in the first line, you can make a Renoir a bit more colorful when you introduce the color of a Gauguin, for instance. So this was, now it's been a while ago, but it was a situation where people started to understand that optimal transport was more than just transporting mass, it was also transporting colors, transporting pixels, transporting whatever you want. And in particular, when you start to get to images, suddenly you end up with having millions of points. And so you see before, I told you, you have 10 coffee shops and 4 bakeries. Now you have 1 million point in one image, perhaps, and 1 million point in the other image, and you start to transport colors or transport pixels, and suddenly, the complexity of the problem increased consistently. This was one example. Then, with going a bit more, let's say, modern, everyone now talks about AI. So there was, in 2014, there is the concept of GAN that was introduced, which is now a very classical concept in machine learning. And the idea is the following. You have, let's say, think of, probably most of you know this better than me, but so you have a generator, which is some, neural network or whatever you have, some system that is able to generate fake images. You have a bunch of real samples. So let's say there I have a million images of real dogs. And here I have a generator which has been trained to create fake images of dogs. And here I have a discriminator whose goal is to discriminate and tell us whether an image that is given to it is either real or fake. And then every time the discriminator gives us an answer, this answer is fed back, so it gives a feedback either to the generator or to the discriminator. In which sense? So let's say the discriminator was wrong, he didn't recognize a fake image, then we give feedback to the discriminator, oh, you made a mistake, be better next time. Or maybe the image was fake, but the discriminator recognized it, which means that the generator has to improve. So to try to pass the test of the discriminator. So the goal here is an optimization problem. You want to make generator and discriminator better and better at create fake images and discriminate fake images. So true is that for most applications, if you think now, now we see it with ChatGPT or all these tools, that what we really want is not really to discriminate image, we don't care too much. What we care is that we are able to generate very faithful fake images. That's really the goal. So more than having a good discriminator, in the end, the goal is really to have a very good generator that is able to generate images which are fake. So what was proposed few years after these GAN models, just in 2017, and then developed further later, was to use optimal transport as a discriminator. So not anymore to have this system of discriminating, but the idea is the following. So let me try to explain this image. So here you have, let's say, some abstract space which what it does, it takes some data in which, okay, these are totally abstract, but then through a map, it creates a bunch of images, okay? Now here you have images that are represented by mu theta. So mu theta is a collection of fake images. And what is your flexibility here? You have a parameter theta, which you can move. Usually theta is very high dimensional. And by changing theta, you can generate different images, collection of images mu theta. Okay, so mu theta is the family of mu images, which depends on the parameter theta. And what is your goal? Is to find theta so that the transportation cost to send the fake images to the real images is the least as possible. So you see, you don't try to do it image by image, but you try to have a bunch of images for each theta, and then you try to make sure that then this collection of images, which are fake, are very close in terms of transporting them to real ones, right? So you see, if the cost to transport a fake image to a real image is small, it means that the images are very close. If the cost to transport two images is high, it means that they're far away. So you use Optimal transport as a faithful control, a control of faithfulness. Okay, so it's just use Optimal transport as a discriminator there to decide whether you are doing well or not. So Optimal transport becomes like your test to decide whether you're approximating well or not good images. That was the idea of Wasserstein-Gunn.
Is it like solving a forward problem and an inverse problem for here?
So when you do usually GANs, you see this is usually always min-max problem that we're doing, where you have usually what people do, right, is a training gradient flow in this kind of training. There, in the original GAN, they had a double problem because they want at the same time to minimize at the degeminator level but maximize the discriminator level because they were competing. Here is just a standard direct gradient flow. You just take your theta originally and you start to modify theta so to make this one smaller and smaller. So there is not really an inverse problem. It's more like that you hide the complexity in this, but then you only have one minimization. It's true that it's a bit hidden because Wasserstein is also a nonlinear object, so I'm cheating a bit perhaps, but people propose that, yes?
What's the role of the costs here? Because that costs are not more appropriate, right?
Yes, so this is a very interesting question. So what cost should I put there? I would say until very few years ago, people just chose one cost and they were happy with that. Like in the original Wasserstein-Gunn paper in 2017, they used the Monge cost, the distance. Why not? They could have said I use distance square. They could have said I use something else. People were mostly using either distance or distance square because they're easy to formulate, they're easy to compute. Now if we go now to real application, not just mathematicians trying to do some theorems, but let's say people who really want to have something efficient, there are better methods than this one, but the cost becomes usually part of the training process itself. So the cost will depend on theta as well, and you try to optimize everything at the same time. So you say, among the possible costs, you kind of give you the freedom to even find the cost in a large space of cost that you don't really know what it is. It's like everything is a black box now, right, with these neural networks. But abstractly, I would say every reasonable cost works. Distance square, they all measure the same. So it doesn't really matter too much. So the fact that, you see, if you tell me the cost to transport is distance or distance square, it doesn't matter in terms of saying whether two images are close or far. I will always pay, if I pay little, the images are close. If I pay not little, the images are not that close. And now, am I using one distance or a different power? They all measure the same quantity whatsoever. Maybe modulo constants, maybe modulo exponents here and there, but being small or large, it's so comparable. Does it make sense? So it depends really what you're aiming for. But if it's just a good approximation measure, no, just use distance, it's fine. After that, there have been other interesting applications. So I chose another one which I think is cool also to describe, which is a nice interplay between math and biology. Because the idea is that this is about single cell genomics. So this is about the fact that when you have cells, when you look at cells, real cells, cells usually have, over time, they can go over mutation stages. So think even in real life, maybe you have cells which are healthy cells, and maybe at some moment cancer may develop. So there are evolutions, right, in cells. And the point when you do, when you study cells, even in labs, what happens is the following. You have a bunch of cells that you have, of which you have a sample. The cells tends to be, so they usually go through mutations because you trigger them in some way. But then once they start this process, the problem is that you cannot observe the cells. It's not that you have a way to really see what's going on. The only way for you to know what's going on in a cell is to take a sample out of it, right? But then once you take the sample is destroyed. It's like when you take from a body, you take a sample cells, you know that you put the cells back on your body. So what you do is that you can, so this means that you cannot take too many of them, okay? You have your cells, you take just a bit small fraction of them, and you hope to, from there to get a good understanding. And so let's say at time t1 you see your cells, and then at time t2 you see them again, and something has happened. They are not the same. And then at time t3 you see a different distribution of cells. So this picture of the landscape that you see on the bottom, this is called Waddington landscape, which is used as an interpretation. Sorry, what's going on? Okay, yes. This is like a model introduced by Waddington a long time ago to just kind of give an additional interpretation of the evolution of cells. So it's not really too meaningful here. But the key point is the following. So because when you measure cells, if you observe them, you kill them, you cannot observe too often. You cannot say, oh, every 10 minutes I'm going to take some cells. It's too much. So usually you have to wait a few hours, sometimes days. You measure once a day. So now the question is, okay, I see some cells there. I see the cells, let's say, 1 day after, and then 2 days later, and so on. What happened in between? And then what Schibinger and his group started to propose, and there has been a lot of work on that in the last years, is perhaps let's use optimal transport to complete the missing points. So I can try, so optimal transport, it has a double feature, right? Once I know, if I think that the way the cells move from time t1 to time t2 via some optimal problem, maybe because I do enough observation and I can find a good model that fits the data, then I just need mu1 and mu-t1 and mu-t2, and I just need to solve the optimal transport problem to know each point at time t1 where it went at time t2. And once I know that I was here at time t1, I'm there at time t2, then I just have to draw a straight line to know what happened in between us. A straight line along this landscape. And this is a way to complete the picture. And that's what people have been doing in this Waddington optimal transport. So they use optimal transport here to complete the picture there. And let me just conclude with one more point, which I think is important because it kind of encodes a lot of the interest that optimal transport now has, not only mathematics, but also outside for real application. And the point is this. So I told you at the very beginning that Kantorovich received the Nobel Prize in economics. And the reason was that he found, he structured optimal transport as a linear programming problem. What does it mean? Optimal transport became a convex minimization problem, thanks to Kantorovich. But if you have a convex problem with n points, then if you use standard algorithms, usually the computational time goes like m cubed. Okay? This means that if you have images of the order of 1 million, you see, 1 million cube starts to get a bit large and takes a lot of time. So because of this, essentially optimal transport was considered very much a theoretical tool, but kind of totally hopeless for applications. Too slow to compute optimal transport. Takes too much time. And around 2013, Marco Couturi made a funny connection because he proposed a new approach to optimal transport, which is called entropic regularization. That, if you don't know what it is, I will not discuss it in details, but if you're interested, there is a very nice book by Couturi and Perret on arXiv, where they describe the computational aspect of optimal transport. And he kind of understood how to make the optimal transport more regular. So let me try just maybe with an image to explain this. So in optical transport, let's say you have mu and you have nu. And what you are trying to do is to find the pairing. Finding the pairing is like in a square, you have to tell me who goes where. The way it works is the following. Let's say that the optical transport map is this one. Then it means that, okay, the mass which is here, it will go in this direction first and then go up. So this is the graph of the map. So I have to find a line inside a square. That's what it means to find a transport. If I am in one dimension. If I am in n dimension, I'm trying to find an n-dimensional object in n times n, in 2n dimension. So usually it's very difficult to find because it's a very low dimensional object. But then what Couturi proposes is to put a small parameter, small regularization parameter, where you're not trying really to find the perfect map, but you're just trying to find some blurry version of it, which then it will be fully dimensional. So like like here, you see it's blurry, but it's not concentrated on a line. It's concentrated now really in blocks. There is something here, something there. So it becomes blurry fine, but then it becomes more spread out. And this is actually rather good. It's good enough for many applications. So you don't find the optimal map. You find just a very regularized version of it. It works really well, actually. And it's funny, actually, that he found in 2013, he wrote the paper. Of course, he created a lot of interest. And then it turned out that what he discovered was something that Schrödinger proposed in 1930. It's called Schrödinger problem, just in a totally different context. And then people made the connection between the two. But the bottom line is that now, with this approach, there are very fast algorithms to compute optical transport. And so this has been a big boom in the OT community, and especially in people using optical transport for real applications. Okay, so I hope at least I gave a bit of overview of what optical transport can do. Of course, I skipped many things, for sake of time. And so I think this concludes my first lecture, and I thank you for your attention.